the frequency ratio R is equal to omega over omega n. We defined it here. And we end up by having, at the end of the day, we end up by having our equation to be me omega square over k. This is nothing but it is force over k, which is basically its static deflection. The force over k is static deflection. 1 minus r squared plus twice zeta r sine omega t minus the angle psi in terms of psi. We have seen this formula last lecture, if you remember, except here we have P that is simply written by m omega square r or E, or m omega square E, where E is the eccentricity, the distance from the center of rotation to the center of mass. Now we write x over me. We can write x over me, where m is the mass of the imbalance, E is the eccentricity. We can write it in this form. Mx over me can be written as m omega square over mk. You simplify m over m, and the omega square over k will give you omega n. So it will turns out to be simply, this one will be r, omega over omega n will be r. So mx over me, the amplitude ratio of the imbalance will be simply r squared over 1 minus r squared plus twice zeta r squared. And if you draw this one for the several values of omega, because here we have in the frequency domain, Shabab, the x-axis will be r, or omega over omega n. That's why we are studying the frequency domain. And then at different values of zeta, you see at resonance, this amplitude will go to infinity when we have zeta is equal to 0. And then it decreases. When you increase the amount of damping, the amplitude ratio will be decreasing. I am increasing the value of the damping. You see that the value of the amplitude ratio is decreasing. So you have to avoid the resonance region, which is omega over omega n is equal to 1, or r is equal to 1. So the amplitude starts by 0, and this is r. When r is equal to 0, it starts from 0. And then when omega over omega n increases, this amplitude ratio goes to 1. So as you can see, the limit, it will go to 1. The only thing you have to avoid the frequency region where r is equal to 1. Similarly, تفضل هاني.
Doctor, so the only I mean, the resonance will happen only if the R is equal to 1 and zeta equal to 0, right?
Yes.
Only this case.
Yes. When zeta is equal to 0, no damping, and R is equal to 1. So when we have damping, the damping try to reduce the motion, the amplitude of the motion. Okay? So this is the resonance case. واضح شباب? Is this clear? Any questions, شباب? So here we have, I think, one example to be solved. Yes, small example to be solved. An electric motor of mass is equal to 500 kilogram is mounted on a simply supported beam with negligible mass. Assume that supporting beam is equivalent to a spring constant K, 4,500 kilonewton per meter, and the damping ratio of 0.1. The imbalance in the rotor is ME is equal to 0.5 kilogram meter. Shabab, this is what we mean by imbalance. Imbalance is always ME, or MR, is mass times displacement. So that's why the unit is kilogram meter. Determine the amplitude of the dynamic amplitude X of the motor when it runs at 950 RPM. So it's a direct application of the formula, the last formula we have seen. We calculate the natural frequency omega n will be K over M, or 4,500 times 10 to the power 3, divided by 500. This will give you 94.87 radian per second. This is shabab the natural frequency, omega n. Now we need to calculate what is the running frequency or the forced frequency. The forced frequency is given by this one, 950. So 950 RPM, 950 RPM, we multiply it by 2 pi and divide by 60 to find the in radian per second, omega in radian per second. So this is omega. So omega is this one, sorry, not omega n, but this is omega. This is omega, the forced frequency. This is omega n, 94.87, and this is omega 99.487. So if you look for the frequency ratio, R is equal to 1.05, which is near resonance, near resonance. قريب من resonance. It's not exactly, but it's near the resonance. قريب. Now, since we have damping, there will be no resonance because the damping here is 0.1, but the amplitude will be still high. We calculate this amount, R squared over 1 minus R squared plus twice zeta R. This is mx over me. R squared, we found it 1.05. 1 minus R squared, which is 1 minus 1.05 squared, plus twice zeta and then R, the whole square will give you 4.72. This mx over me is equal to 4.72. From where you can solve for x alone, you can solve for x. X will be equal to simply 472 multiplied by me divided by the mass m. واضح شباب؟ تسوي لي فن. We did it this way, me divided by me times mx divided by mx. mx over me, this one, the whole thing is 472. Multiplied by me is given to be 0.5. Divided by m is 500. So x will be 4.72 times 10 to the minus 3 meters. So the amplitude of the output will be 4.72 millimeter. واضح شباب? So now if this one is near 1.05, you will go here. 1.05 will be sometimes like near this one. And the damping ratio, we found it to be with the damping ratio, we found it to be 0.1. So the amplitude will be something like here, 4.72 millimeter. واضح شباب? This is 1.05 R. R is equal to 1.05. Zeta is equal to 0.1, corresponds to this curve. I'm not sure if it is clear for you. So zeta, so if you take a vertical line here, you take a vertical line and you will see, you draw a horizontal line from here, you draw a horizontal line. So you will see that you are at somewhere in a 4.72. Either you can use it graphically or you can use it with the formula. The formula gives us this value. Graphically, will give you approximately the same value. So hina zeta is equal to 0.1. And R is equal to 1.05. With these values, zeta is equal to 0.1 and R is equal to 1.05. We found for the X, the amplitude is equal to 4.72. Any questions, Shabab? This is what we found here, 4.72. Any question? Any question? Now we have what we call vibration isolation. vibration isolation. What is vibration isolation? Sometimes you have, Shabab, a machine that is working, working, and this machine, you put it on the ground, and the machine can transmit motion from the machine to the ground. So we usually, what we put, if the motion is transmitted from the machine to the ground, so you don't want to damage your ground, you put an isolator. This isolator is simply a spring and then damper. That's why we call isolated systems. Or sometimes the machine, or when the machine is moving and it transmits force to the ground, you will also put the isolation system. So force from the machine to the ground, or the ground is moving, like we have seen it in the, if you remember, when we studied the suspension system, the ground was moving and it transmits forces to the system, to your machine. So you want to avoid that. If the ground is moving, you don't want this motion to be transmitted to your machine. So we will put, in both cases, we will put isolator, that is damper and then spring. Damper and then spring, called isolated systems. Is the idea clear, Shabab? In both cases, we have either the force that is transmitted from the machine to the ground, or the ground is moving, the base is moving, and we put, it's transmitting a force to the, or motion, it is transmitting a motion to your machine. In both cases, we will put the isolator, which is a spring, and then a damper. So vibration isolation is a process by which vibratory effects are minimized or eliminated. The function is a vibration absorber. What is an isolator, شباب باللغة العربية? Isolator.
عازل.
Do you agree with your answer, Shabab? One of your friends, isolator. عازل. Sometimes you hear the word عازل حراري or عازل like this. So you isolate واحد مريض يكون في المستشفى, they isolate him. They يعزلوه على ما يعديهم. فهذه we call it عازل. فهذا spring and damper يعزل the vibration that goes either from the machine to the ground, or the motion that is coming from the ground to the machine. We put this one. So to reduce the magnitude of force transmitted from a machine to its foundation, or to reduce the magnitude of motion transmitted from a vibratory foundation to the machine. So this is the figure 911. It illustrates the cases. I already mentioned this one. So we will see, Shabab, we cannot 100% reduce the transmitted force or transmitted motion, but at least we should reduce it. We will see how much we can reduce it. These are some examples of the isolation system. Usually we will use the, in our course here, we will use the passive isolator. Passive ones, it consists of resilient member, which are stiffness, and energy dissipator, which is a damping with constant properties. Examples are metal springs, cork, felt, pneumatic springs, elastomer, rubber spring, and so on. Active one, they are external power is required for the isolator to perform its function. An active isolator is comprised of servo mechanism with a sensor, signal processor, and an actuator. So these are some isolators that we put under the machine. Maybe you have seen, if you go to Aramco or big companies, you will see this isolator are put here. عبارة عن springs, and then inside there is a damper. So the typical vibration absorbed isolator is shown in this figure. We can put it this way. In a simple vibration isolator, a single element like synthetic rubber can perform the function of both the load supporting means and the energy dissipation. So we call transmissibility, it is a measure of the reduction of transmitted force or motion afforded by an isolator. Transmissibility, how much is transmitted, how much force is transmitted, or how much motion is transmitted. For the system shown in figure 910, the previous I have showed you, the source of vibrating is vibrating force resulting from unbalance of the machine. The transmissibility in this case, the force transmitted ratio is given by amplitude of the transmitted force divided by amplitude of the excitatory force. So Ft over F naught is given by this amount, transmissibility ratio. Here, if we have this one, if you remember, we have just seen the rotating unbalance. The excitatory force, the exciting force was given by this one, m e omega square sine omega t is equal to F naught sine omega t. So we can write this term, we can write it m e omega square, we can write it F naught. So this will be the input to the system. So the unbalance is causing vibration to your system. So your equation of motion, if you remember, we wrote it in this form, mx double dot plus bx plus kx is equal to p of t. M is the total mass of the unbalance, including the mass m. So here, Shabab, we write the force transmitted to the foundation is the sum of the damper spring and the spring force. Then, if we write the free body diagram, you will see that this one can be written as a force coming from the damper and force coming from the spring. And this force, as the output, as this, we can write it Ft sine omega t plus phi. So it is transmitted. So the force or the resulting force will be of this type. F, since we are dealing with forces only, so this will be Ft sine omega t plus phi, like we have seen in the previous lecture. Now, if we take Laplace transform of this and this, the first one will give us Laplace transform ms squared plus bs plus kx of s is equal to p of s. The second one here will give us bs plus kx of s is equal to f of s. Now, if we would like to see what will be the ratio of the transmitted force over the input force, we have x of s over p of s. You solve for this one here, x of s over p of s will give you this, 1 over ms squared plus bs plus k. And now, if you want f of s over x of s will be 1 over bs plus k. And if you want to take x of s over p of s, or x of s over f of s, this will give you the following. Now we can write force p f of s divided by p of s. It will be f of s times b divided by x of s multiplied by x of s over p of s. لأنه هنا we can just cancel x of s and x of s, and we have the two forces. So we already calculated f of s over x of s. We calculated x of s over p of s from the previous slide. So at the end, we will find bs plus k over ms squared plus bs plus k, which is the transmitted force over the input force. So if you now take the sinusoidal transfer function, just substitute s by j omega, and you will find this bg plus k over minus m omega squared plus bg omega plus k. Just substitute substitute s is equal to j omega. So if we do the same substitution before also, we introduce these quantities, omega n squared is equal to k over m, and b over m is equal to twice zeta omega n. We can write it in a simpler form just by doing 1 plus j twice zeta omega over omega n, and 1 minus j, 1 minus omega over omega n squared, plus j twice zeta over zeta omega n. Now, if we want to take the magnitude of this, amount, magnitude of this one, you take the magnitude of the input, magnitude of, numerator, over the magnitude of the denominator. Here, the real part will be 1 squared, plus the imaginary part will be twice zeta omega n the whole square under the square root. This is the magnitude of the numerator. Magnitude of the denominator will be this one square, the whole thing square, 1 minus omega over omega n square, plus this one square, or the magnitude of this one. So at the end of the day, we put R is equal to omega over omega n, which is the frequency ratio, and we end up by having this 1 plus twice zeta R, the whole square, over 1 minus R squared plus twice zeta R squared. And this will be the amplitude ratio of the output force over the input force, which is this one. Now, the amplitude of the excitatory force is F naught PG omega, and the amplitude of the force transmitted is FT JG omega. So we have the transmissibility ratio is written like this, FT over F naught, which is equal to 1 plus twice zeta R squared over 1 minus R squared plus twice zeta R squared. Now, Shabab, we will see the amplitude ratio, how we can draw this amplitude ratio. You see that this amplitude ratio, TR, or the transmissibility ratio, is depending on zeta, and it is depending on R. You have to avoid when R is equal to square root of 2, we will see what will happen, and R, when TR will be equal to 1. If we see the plot here, this is what we will see. This is the amplitude ratio. So, Shabab, here you will see that for any value of zeta, any value of zeta, all the curves pass through this point. We have the amplitude ratio TR is equal to 1. TR is equal to 1, and zeta is equal to, or R, R will be equal to square root of 2. R will, so this point, I am talking about this point here. For any value of zeta, we have R is equal to square root of 2, and the amplitude TR is equal to 1. So this one, any value. Now, the values TR, this TR is greater than 1. TR is greater than 1 if zeta is less than square root of 2. So TR is greater than 1. So in this case, there will be what we call amplification ratio. Amplification. TR is greater than 1 if omega or R is less than square root of 2. What will happen if R is greater than square root of 2? If R is greater than square root of 2 here, this value, you see that this TR is less than 1. Is less than 1 معناته هنا there is a reduction or isolation, and the amplification or amplitude of the output is smaller than 1. So it is reduced. So it is reduced. So if you increase the value of R, or if you increase the frequency of the input, you will have reduction. The magnitude will be reduced. As long as you are greater, the amplitude will be greater than square root of 2, you will have reduction. The magnitude will be amplified, yani the output amplitude will be greater than the input amplitude when the ratio R, or the frequency ratio, is less than square root of 2. So بيت القصيد كله هنا is at square root of 2. When this frequency ratio is greater than square root of 2, you will have isolation. And the vibration of the output, amplitude of the output, will be smaller than the amplitude of the input. At when zeta is equal, for all values of zeta, of course, the value when zeta is equal to 0, when zeta is equal to 0 and R is equal to 1, still will give you the resonance. You have a resonance point, that is this one. This is the resonance line. Here you can see when R is equal to 1 and zeta is equal to 0, you obtain a resonance line. So a resonance. You have to avoid it. But now we are interested in reducing the vibration. If you want to reduce the vibration, you need to have R greater than square root of 2 in this region. So if R is less than square root of 2, you have amplitude. So the ratio is greater than 1. The ratio is greater than 1. The ratio is greater than 1. You have to be careful. And of course, at R is equal to 0, the ratio is 0 also. So since we have the amplitude, the input is equal to F naught ME omega squared, so the force transmitted will be ME omega squared times the transmissibility ratio. لأنه هذه we wrote it F T over F naught. This ratio كتبناها this ratio شباب 1 plus twice zeta R the whole square divided by 1 minus R squared the whole square plus twice zeta R the whole square. Now this guy, since this guy is equal to M E omega square, you can take it here and you will obtain this equation. So this will be, in this case, you will see the transmitted force to the ground. What transmitted force to the ground? The value of the transmitted force to the ground. An example here, suppose a machine is mounted on an elastic bearings, which in turn sits on a rigid foundation. The bearing damping is negligible, yani damping in a 0, zeta is equal to 0. In operation, the machine generates a harmonic force having a frequency of 1000 RPM. So omega will be 1000 RPM. Omega, this is the forcing frequency, RPM. If the mass is 50 kilogram, mass is equal to 50 kilogram, find the condition of the equivalent spring K of the elastic bearing for suppression. For suppression means reducing the force of the transmitted force. Also find the percentage of the dynamic force generated by the machine that is transmitted to the foundation if the stiffness of the bearing is K is equal to 200 kilo Newton per meter. هنا شباب, we need to find the condition for suppression. The condition for suppression, we have R, we said should be greater than square root of 2. R should be greater than square root of 2. This will give you the suppression or will give you the reduction. So, you know, simply R is equal to omega over omega n. This is the ratio. And this one should be greater than square root of 2. If we solve for omega n here, you know, if we solve for omega n, we know that omega n will be less than omega over square root of 2. Omega n is simply K over M, should be less than omega over square root of 2. Now, Shabab, we have this one, if you remember, this is the condition, we have found it here. And omega, the forcing frequency, is given by 1000 RPM, yani 1000 times 2 pi over 60, which give you 104.7 radian per second. This is the operating frequency. Now, if we substitute in this equation, if we substitute for the values of K and for the values of M from this equation here, we will find the following condition here. We'll find omega n will be K over M, or 104 is the frequency, divided by square root of 2. This will give you 74.05 radian per second. Yani if you solve for K, if you square both sides of this equation and solve for K, you will find K should be less than M times omega n squared. K is given to be 50. Omega n, we just found it to be 74.05. So the stiffness should be less than 274 kilonewton per meter. The desired condition on the stiffness. So to have this suppression or to have isolation, we should have the stiffness should be less than 274 kilonewton per meter. Now, this is the condition that will give you suppression. Now, if he gave you K is equal to 200 kilonewton per meter, does it satisfy or does not satisfy, Shabab? Can you please answer this question? The condition for suppression or for the isolation is 274. Who he gave 200? Does it satisfy?
Yes.
Yes, it will satisfy. So you see here, Shabab, since he give you the 200,000 or 200 kilonewton per meter, you divide it by m, you will get 63.1.52. If 63 radian per second, you divide omega by omega n, and you will find ratio is 1.657. This ratio 1.567 is like this, is here. Here we have square root of 2. Square root of 2, Shabab, this is the isolation region. Square root of 2, usually it's written by 1.414. So square root of 2, this is 1.15. Now we found r is equal to 1.6. 1.6 is here. So you are in the isolated region. So 1.6, you are in the isolated region, and the transmissibility ratio in this case, if you look at it, it will be 1 plus twice zeta r under the square root of 1 minus r squared plus twice zeta r squared. This will give you 0.573. يعني basically 57.3 of the machine generated is transmitted to the foundation. The force that is transmitted to the foundation will be 57.3%, which is this one. واضح شباب؟ So the question is here. تفضل هاني.
دكتور هنا عندنا 57 right percentage.
Yes.
I mean, is there any general desired percentage of transmissibility, or depends on the application of the industry?
Depending, no, not really, because it depends on the machine, the component of the machine. Some equipment will have desired value. They want to operate in this value, for example. They want to be here in this region. Some companies, they want, because they are sophisticated machines and they don't want certain percentage. They want to be, they will tell you, I want to be here in this region. If you look here, now what we found now today, we found just 1.6 is somewhere here. 1.6. 1.6, if you look here, it will give you, if it will give you like 57%. From here to here is 1. So here at this point, it is around 57% or 0.57. But some companies, they want it here to be minimum as possible. Yeah, there are some restrictions for some companies. But as a general problem, as a general rule, as long as the frequency ratio is greater than square root of 2, you are in the safe side.
Okay, clear. Thank you.
Another problem, Tina, to close this subject, the following data is provided for the system shown in the figure here. We have capital mass is equal to 15 kilogram, B is equal to 450, C 6 kilonewton per meter, M, which is the imbalance 0.005 kilogram, E is 0.2 meter, and omega is equal to 16 radian per second. The equation of motion is written like this: mx double dot plus bx dot plus kx is equal to me omega square sine omega t. Here they are looking for the force transmitted to the foundation. So if we substitute these values, we will get 15x double dot plus 450x dot plus 6000x is equal to 0.005 times omega e, omega square 16 times e 0.2 sine 16 omega t. So omega n, the natural frequency, will be k over m, or it will be 20 radian per second. Twice zeta omega n, or the damping, will be 450 divided by 15. So from here you got the damping, which is 0.75. The frequency ratio is 0.8. R will be omega over omega n. So here, from this equation, if you remember last slide, I gave you this. The transmitted force will be me omega square multiplied by this ratio. This ratio, you have all the ingredient. You substitute, you will find that 0.319 Newton is transmitted. 0.319 is transmitted to the foundation, which is small force. Yani basically 0.319 is just as if you throw 3 kilogram تقريبا 3 kilogram on the foundation, which is a small amount. This is when we have force transmitted. Next lecture we will see when the road profile is moving and how this motion is transmitted to the car or to the machine, to the foundation. By the way, this is not my car. Don't think that this is my car. If my car this was this one, you may not find me here maybe. Okay, Shabab? Maybe this car is for Hani al-Rumayh. This is Hani al-Rumayh car. Inshallah, in the future. I hope he will own this car one day.
You won't find me.
Yeah. Hani, if you get this car, just take me in the ride.
Yeah, I will give it to you a week.
No.
But give it to me and we will discuss it.
Inshallah. Shabab, next time, inshallah, we will continue this slide. We will see how the motion is transmitted to the car. Let me just take the attendance. Shabab, I am preparing some old exam problems for you, and I will post them, inshallah, tonight. Regarding chapter 6, chapter 7, and chapter 8. I'm preparing them. I'm preparing, inshallah. I will post them tonight. Just after this lecture, just try to go through them. They will help you a lot. It will help you. It will help you in solving, because so far we did not get the textbook. صح? You did not get the textbook.
No.
So let me at least solve some old exam problem, and then we will try to be on time, to be on the picture, to be. So you will حتى ما تجيكم مفاجأة يعني في الامتحان, or you will say we did not solve this or we did not solve this. احنا in the lecture we are very tight. We cannot solve too many problems, but inshallah we will complement this by giving you the solved problems. العلوة منير معنا اليوم. منير كيف حالك اليوم؟ إن شاء الله بخير. البغالبي فيصل، كيف درجة الحرارة عندك فيصل اليوم؟ المسعودي سعودي عبد العزيز 43 ما شاء الله. احنا هنا في الظهران أعلى من هذه. الملاح ماجد
موجود دكتور.
كيف درجة الحرارة عندكم؟ نازلة ولا طالعة؟
طالعة أكيد.
يمكن انت داخل المكيف ما تحس. حسين القحطاني
موجود.
خليل حسين. المحمدي عبد العزيز. عبد العزيز كيف حالك اليوم؟ ان شاء الله بخير.
بخير الحمد لله دكتور، انت كيف حالك؟
القحطاني عبد الكريم الله يبارك. القحطاني عبد الكريم. عبد الكريم سلامات، ما شفتك امس. او نسيت المحاضرة.
دكتور نسيت الكلاس.
اوه الله يعني. وما انسانيه الا الشيطان. استعذ بالله، قول استغفر الله. الشهري علي. الشهري علي كيف حالك الشهري علي؟ الرميح. وينك الشهري؟ وين جالس الآن؟ في جدة ولا في مكة ولا وين؟ علي ما شاء الله، المدينة المنورة. ادعينا عند رسول الله، هم فتحوا لكم المسجد ما شاء الله، تروح تصلي هناك وادعونا معك. القرني علي
موجود دكتور.
القرني علي كيف حالك؟
تمام الله يحفظك.
الزهراني فارس
موجود.
فارس ما شفتك أمس، وينك؟
والله يا دكتور توي دريت انه في امس دوام.
الحمدان عبد العزيز. عبد العزيز وينك أمس؟ ما شفتك.
والله برضو دكتور ما كنت أعرف صراحة. يعني ما ارسلت ايميل ولا. الله يعطيك.
هو الاصرار اللي حط، مش انا اللي هو اللي حطها. انا كان بودي ما نحضر لانه اتس ويكند. بس المشكله حطوا لنا هذا اليوم. العجمي مبارك موجود. مبارك العجمي، مبارك العجمي. الطليحي يوسف، يوسف أنت معنا؟ إذا ما كنت معنا عن هذا يا يوسف.
موجود.
طيب الزاير حسن، ما شاء الله الزاير يرفد يقول لي حاضر قبل ما أنطق اسمه، يعني عارف رقمه في النمبر. الجهني نادر.
يا دكتور.
أهلا وسهلا. كيف هو الجهني نادر اليوم؟ سلم لي عليه إذا شفته.
يا دكتور.
العقيل، خلوني أكمل يا شباب.
دكتور بس اسمي أنا الظاهر أنك مشيت عنه.
مين؟
محمد الشريدة.
كم رقمك؟
ما أدري بس اللي أعرف أنه قبل يوسف.
لا حذرتك.
يعني نطلع خلاص.
حذرتك وانت قاعد تتهم فيا بجزاف كذا، انا ما.
إيه زين أنا ما سمعت اسمي. يلا يعطيك العافية دكتور.
الله يعافيك. يلا الجهني نادر. اهلا وسهلا. العقيل رائد.
موجود رائد موجود.
اهلا وسهلا.
موجود.
شرفنا حسين.
هلا.
حاضر دكتور.
شيخ حسين كيف امورك؟ ان شاء الله تمام.
دكتور يسكيب ماي نيم.
دبيس علي.
دكتور يسكيب ماي نيم. دبيس موجود.
اهلا. مين اللي يقول لي يسكيبت ماي نيم؟ مين؟
عبد الله درويش. بعد رائد.
عبد الله درويش.
بعد رائد رقم 2 رقم 20.
رقم 20.
ايه
الدرويش هذا. لا ديد نوت سكيب. حضرتك.
اوكي شكرا.
تتهم فيا بالاتهامات الباطله هذه، الله يسامحك. البشر علي.
موجود يا دكتور.
اهلا وسهلا.